So thank you all for being here. Excited to see such a vibrant audience. So the goal, or I wanted to talk about scaling up and lessons learned and some of the things that we've been doing over the past 2 years or so in this field. The organizers already did such a good job of talking about scaling up. So some of this might be a little bit redundant, but just trying to provide some additional context on where we're at, what are some of the goals, why do this, and what it can actually tell us potentially about the brain and function. So, all right. So I think all of us are, on board with the idea that the brain is a very complex and high-dimensional system. And, in order to deal with this amount of complexity in neuroscience, we often try to, build relatively controlled experiments that give us a picture of the brain in a particular context. And then from that, we want to come up with some simple explanations for our data, right? And I think that we've seen a number of different instances, Hee-Woon and Weasel, right, of where we can actually, say or build insights into the functional properties, say, of different brain areas, as well as come up with theories and understandings of how neurons work. But as we've started to, see the brain in its kind of more intrinsic complexity and, all the different ways in which a neuron could potentially function, I think that we've come to this sort of understanding that in many cases, simple models might not tell us the full picture of what's going on in the brain. And so in many different fields, we've, kind of come to this conclusion that often the key for understanding complex systems is not often by, understanding or being able to have a simple explanation, but instead often just allowing models to learn directly from data. And in particular, we need models that allow for the type of scale that can give us insights into the complexity of this system. And so Rich Sutton, has a really brilliant piece where he talks about this bitter lesson that we've seen in many different fields. And he writes that the actual contents of minds are tremendously complex, and we should stop trying to think of simple ways or find simple ways to think about the contents of mind, such as simple ways to think about space, objects, multiple agents, or symmetries. They're not what should be built in, as their complexity is endless. Instead, we should try to build in or build the meta methods that can find and capture this arbitrary complexity. And recently, Blake and I put together a piece in the transmitter that kind of goes deep into the bitter lesson and how this, could be applied also within neuroscience. And so, if we look at this lesson that we've seen time and time again in different domains, we think that similarly in neuroscience, because we're dealing with very complex high-dimensional systems, it's likely that scale will also be an important ingredient in building a more generalizable understanding of brain function. And as we saw also in the opening remarks, I want to kind of mirror this same way of thinking about things. So, as we scale, this will allow us to kind of algorithmically stitch together different data sets that are spanning different brain regions across different animals and tasks. And so as we've seen, there have been over the past, really rapid progress over just the past 2 years in building models that allow us to start to explore these many dimensions of scale. And so we see here both, massive growth in the number of subjects that we're able to stitch together or build models across, now on the order of hundreds of animals, as well as the amount of recording time and hours that have gone into these models as well. And so we can see that really we're just scratching the surface in terms of this scaling. We have, actually very large repositories of data coming from, coordinated efforts like the International Brain Laboratory, as well as the Allen Institute. And we're going to hear from some of our speakers today from both of those projects that will tell us a bit more about, what's coming out, and all the other data that we might not already have been able to access. As well as Dandy, which is a repository of many different data sets from different labs. And so this gives us a really large swath of potential data that we can use to scale up these models. So in total, if we look at many of these large efforts as well as Dandy, we see that there's nearly 8,000 hours already of publicly and open available data sets. And I think there's even more that's yet to be released. And so we're excited about working with these different groups to be able to, start to train models on all of this data and potentially really test the benefits of scale. So in terms of, as we start to, really move towards this effort of being able to scale up neural data analysis, there will be a number of things that we're going to need. So we have heard about, a number of models in the previous talk or in the opening remarks, and we're going to also hear from a lot of speakers talking about different methodologies and tools for training on large amounts of data. Of course, we need data. We need potentially a lot of it. We have, as I just showed, about 8,000 hours worth of recordings, but it's still unclear how much data we're actually going to need to be able to achieve some of these goals. And in addition to, models and data, of course, we'll also need massive amounts of compute. And this is currently a challenge, especially in academia, right, where we don't necessarily have access to the large scale GPU infrastructure and resources that they have in industry. And so I think as a field, we're going to have to grapple with some of these challenges and think about how we will achieve this goal. And so, scaling is challenging in general. And in particular, in neuroscience data, we have really unique data formats that are quite different from the sorts of challenges that people have faced, say, in language models, which have a relatively homogeneous format, right? From different documents that might describe, different sources of information, but it's all text at the end of the day. And so the way that people have gone about tokenizing and building models for language models, I think, is quite different from the challenges that we'll face. And in particular, in neuroscience, we have data sets coming from different experiments, from different tasks with completely different design, but also it's very multimodal, right? So we have not just neural data that we're recording from, but also different forms of behavior. And this contains both events as well as regular time series, as well as, really kind of complex trial structure within the data. And so having efficient ways to train these sorts of deep learning models on neural data, we think could really help to accelerate science. And so I thought the one thing that I was going to talk about that was different from the opening remarks was some new tools that we've been developing for this, but they also talked about torch brains. So, but yeah, I just wanted to tell you all that, in order to, start to accelerate the field and to help to, bring a lot of these different challenges, into a kind of common framework and allow for this sort of scaling. We've recently released a few different packages for training deep learning models on neural data. And we really hope that this can be kind of the beginning of helping the field to start to scale up and solve a number of these challenges. And so I was fortunate to present a tutorial at the beginning of the main meeting. And so if you weren't there for that, we did a deep dive into these different tools and also released a number of notebooks for the community as well, which we think will help to kind of get people going on this. So the tools consist of three main packages. The first being a toolbox that allows for efficient extraction of information from these complex multimodal data sets. So this package called temporal data. One of the features of it is, often neural data sets can be really big and kind of unwieldy, and you can't actually load all of this into memory. And so what temporal data allows us to do is lazy loading to basically extract out, snippets or small pieces of the neural data, which can be used for training deep learning frameworks. And so temporal data goes into this package that we call TorchBrain, which is a PyTorch-based library for building any number of deep learning models on neural data sets. And I'll go into a few more details. And then finally, we've also been putting together a collection of prepared data sets, so brain sets, to hopefully help with reproducibility and provide data sets that people can test their models on along with other benchmarks and existing models. And so as I sort of already motivated, temporal data allows us to do, slicing of data sets, lazy loading, and also allows for a number of different set operations that can allow us to find, chunks of data that have certain properties, like only during the trial or only during certain reaching tasks. And so TorchBrain, is designed to be flexible, efficient, and scalable, and really allows for a number of different easy specification of data loaders and samplers, as well as a number of tokenizers, different tokenizers for neural data. We provide kind of standard augmentations that can be leveraged in many of these different models. And we also have a model zoo. Right now we have Poyo and Poyo Plus, but over the next months, we're going to be integrating a number of other mass modeling approaches, including some of the ones that we saw in the opening remarks. And really, we hope that this can be the beginning of a community effort. And so we would love to talk to you about integrating your models into this framework so that more people can access them and be able to use them easily. And then, within brain sets, we have a number of existing data sets, mainly from data that went into the training of Poyo, so non-human primates in a lot of motor contexts, but we're also preparing a number of IBL, Allen data sets, as well as trying to put in some of the Falcon benchmark data sets as well, so that this can be a really reproducible set of tools and data sets for the community. Okay, so with that, I wanted just to spend a little bit of time now talking about some of the ways in which we think that these types of large-scale models can potentially be used to understand aspects of the brain. And so what does this actually tell us about brain function? And I think, there's been over the years, even before we started doing this on massive data sets, which of course could be even more complex to potentially understand, I think there's been, some pushback on using deep learning models for understanding neural data in general. And so we think that, while this isn't going to solve all of these questions, right? Training on large data sets isn't going to necessarily tell us immediately how the brain works and its function. There's a number of things that we think are kind of important starting points towards this end. And so in particular, with a large model trained on many diverse data sets, we'll have a way of mapping many neural recordings into a common latent space. And I think that this opens up a number of avenues for comparative data analysis. So, asking questions like, how does the brain function in one individual, or how does one task fit into the landscape of, other tasks or across many different animals? How similar are two brain regions and how they drive behavior? And what is the variability due to differences across individuals versus differences across areas? And only with training on many data sets that have these diverse tasks or are trained across many individuals will we be able to effectively answer some of these questions involving comparative data analysis. In addition, I think that there's you know, a kind of exciting approach where if we could potentially have a very large emulator of brain function, so something that could very effectively predict and forecast what neural activity looks like, then we could also use this emulator to test a, you know, kind of almost infinite battery of different perturbations. So modifying neural patterns at the input and testing how this changes the output of neural activity and behavior. And we know that causal, or, you know, these sorts of perturbations within the nervous system can give us a lot of insights into neural function, but of course, the amount of times that you can perturb the neural state is limited, and tools to do that are still, you know, kind of up and coming. And so really this would be a way to kind of synthetically test all of these different possible combinations and understand what that gives rise to in terms of behavior. And so this would give us a generalizable simulation of brain function that we hope can capture both common and shared principles, as well as account for individual differences and variability. And so really, I think that this, the premise of this is that instead of trying to, you know, simplify or come up with a simple explanation for brain function, instead we propose to kind of embrace the complexity of brain function. And I think that, you know, as we saw a shift, you know, even in this community towards neural population dynamics, right? The insight was that maybe the function of individual neurons won't tell us the full picture of computation. So instead we said, okay, now we need to look at populations of neurons, right? But maybe we actually need to look at even larger populations of neurons that might be spanning many brain regions. And we know that currently that's not feasible to do within a single experiment. And so I think that if indeed we need to understand or, you know, be able to capture the activity of very large populations distributed across the whole brain, then we might, you know, kind of, this might necessitate a need for algorithmically stitching together all of these recordings to really see the bigger picture of that neural computation, potentially to see the sort of computations emerge at that scale. And so currently, we don't know what we may learn with a model of whole brain dynamics, but it seems like AI might be the only way to try to attempt it. And with that, I'll end and open it up for questions. Thank you so much.